Hey guys, it's Miss Johnson and I'm here to bring you our notes for Unit 6 Learning Target 6. Today we are going to talk about exponential decay. So in our last lesson, we talked a lot about exponential growth. Today we're going to look at the flip side of that and talk about exponential decay. So exponential growth was things increasing, exponential decay was things decreasing. And all of these are over time. So increasing over time is growth, decreasing over time is decay. So here's our equation. It's going to look very similar to the exponential growth equation, except for we are going to be starting with 100% of our situation, whatever our thing is that we're looking at. We start with 100% and subtract the decay rate. So instead of adding the growth rate, we're subtracting the decay rate. So that's what makes it exponential decay. Everything else is the same. C is the initial amount, R is the rate of change, and you have to write it as a decimal. T is our factor of time. The other thing is that the C value is also the y-intercept, and that is still true. So everything else stays the same, but this piece right here is 100% of our whatever we're looking at minus the growth rate, or in other words, 1 minus R as a decimal. So let's talk about how we would graph these things. So we want to write an equation to start, and then we are going to put it on a coordinate plane. So let's just remind ourselves, we have y equals c times 1 minus r to the t power for our equation. In this case, c is 16 and r is 0.45. So I'm going to have y equals 16 for my starting amount, 1 minus 0.45, and then we raise that to the t power. All right, so now let's go ahead and make our graph. So we're going to have our same x values that we always use, -2, -1, 0, 1, 2, 3, and then we go ahead and plug them in. So I'd have y equals 16 times 1 minus 0.45 raised to the -2 power. If you don't have your calculator out already, go ahead and grab your calculator. You're going to need that today. So I have 16 times, open a parenthesis, 1 minus 0.45, close a parenthesis, raised to the -2 power, and I get 52.89 there. And then I'll type in with the -1 power, and I'm just going to go down the line of my x values. For -1, I have 29.1. For 0, I have 16, which we should expect because when we raise anything to the 0 power, all of this stuff would go away and you're left with that. Now let's go to the first power. I get 8.8 there. I'm going through these rather quickly on my calculator. Please make sure that you're trying them on your calculator so you know you are getting the same results I am, so you know you're typing it in the same or the correct way. So to the third power, 2.66. Okay, so those are my y values. Now I want you to pay attention to something. See how you start up at 52 and you move down to 2.6? That's the decay part. It's decaying, it's coming down, okay? So if I try to put these on a coordinate plane, -2 is way, way, way up at 52. I can't even graph that. So -1, I'm up at 29. Here's 19. 29 is going to be like way up there. I might not even be high enough there. 0 is 16. So 16 is right there. 1 is 8.8, right about there. 2 is 4.84, right about there. And then 3 is 2.66. Okay, so now if I connected these, it's going to come down. And here's where it's going to turn and level off to the x-axis that way. Okay, there's the decay. It's going down. Decreasing. Okay. Let's take a look at number 2. I have c is equal to 15 and r is equal to 30%. Remember that we need to change that into a decimal, so I'm going to go back 2 places and call that 0.3. So my equation looks like y equals 15 times 1 minus 0.3 raised to the t power. -2, -1, 0, 1, 2, 3. all the way down. And again, this is decay, so I'm subtracting there in the middle. So my first one would look like y equals 15, 1 minus 0.3 raised to the negative 2 power. I'm going to go ahead and plug that into my calculator. 15 times, open a parenthesis, 1 minus 0.3, close a parenthesis, raised to the negative 2 power. I get 30.61. I'm going to enter in my negative 1 power, and I get 21.43. And again, I want you to type these into your calculator to practice and make sure that you are entering them in correctly into your calculator. Obviously, 0, we should get 15. Power of 1, 10.5. Power of 2, 7.35. Power of 3, 5.145. So again, you can see that the values are decreasing, okay? They're going down. So at negative 2, I'm up at positive 30, which is going to be like way, way, way up high in the air. Negative 1, I'm going to go to 21.4. So 21.5 is right about there. 0 is 15. 1 is 10.5. 2 is 7.35. 3 is 5.145. So this one is a little bit more gradual of a decrease. It doesn't decrease quite as much as the other one did. So it's going to level off eventually, but it's just doing it a little bit more gradually. But it's still going down. Still values that are decreasing. All right, so now let's put these into practice in some application questions. It says a fully inflated raft loses 6.6% of its air every day. The raft originally contains 4,500 cubic inches of air. Write an equation to represent the loss of air using the general equation for decay, and then estimate how much air will be lost after 7 days. Okay, so this is going to be similar to what we did in the exponential growth questions. We're going to write the equation first. So up here, we're just looking for the basic y equals c times 1 minus r raised to the t power. All we're looking for is the equation. And then we're going to use that equation and apply it in part B. The two things you need to know are the c and the r. So I see right here is that the raft loses 6.6% of its air every day. So I'm going to say that my r is 0.066 because I need to move my decimal point back 2 places. And then I see that it originally contains 4,500 cubic inches, so that's my c. So my equation looks like y equals 4,500 times 1 minus 0.066 raised to the t power. Then, so that's my equation for part A. Then in part B, how much air will be lost after 7 days? You've got y equals 4,500 times 1 minus 0.066 raised to the 7th power. I'm going to type all that in. 4,500 times 1 minus 0.066 raised to the 7th power. I get y equals 2,790.2. This is... So we're in cubic inches, which means I would write inches to the 3rd power. Okay. Let's take a look at number 4. During the past several years, the population of Campbell County, Kentucky has been decreasing at an average of 0.3%. Be careful there. 0.3% per year. In 2000, the population was 88,647. So write an equation to represent the population. Okay, the first thing, when you look at that percentage, you've got 0.3%. Your decimal point, because there's a percent sign, it still needs to go back 2 places. So your R is equal to 0.003. And then in 2000, you've got 88,647, that's going to be your C. So my equation looks like y equals 88,647 times 1 minus 0.003 raised to the t power. That's my standard equation for that situation. Now, I want to estimate, assuming the trend continues, estimate the population in 2013. So this was 2000, now I'm looking 2013. The time that has passed, remember we talked about We talked about that in our exponential growth equation lesson. So 2013 minus 2000 is 13 years. So I'd have y equals 88,647 times 1 minus 0.003 raised to the 13th power. Okay, 88,647 times 1 minus 0.003 raised 13. So I get y equals 85,251.32, or 317, I should say. These are people. This is population, which means I have to round to the nearest whole. So that 3 is going to tell me to keep it the same. So I would label this as 85,251 people. All right, let's take a look at number 4. So during an economic recession, a charitable organization found that its donations dropped by 1.1% per year. Before the recession started, its donations were $390,000. Write a decay equation. Here's my C. This is my R, but I need to move my decimal back 2 places. So my R is going to equal 0.011, which means my equation looks like this. 390,000, I should say y equals 390,000 times 1 minus 0.011 raised to the t power. Then it says, estimate the amount of donations 5 years after the recession started. So this one, you don't need to figure out how much time has passed. They're just asking for 5 years. So t equals 5. That's y equals 390,000 times 1 minus 0.011 raised to the 5th power. So type all that into your calculator. 390,000 times 1 minus 0.011 raised to the 5th. I get y equals $369,016.74. This is money, so I'm going to label it with a $sign. And there's my amount. Okay, so let's just talk a little bit about how we would determine the difference between growth and decay. So now you are going to be asked which one is it? Which one does a certain situation fall under? And here's how you determine. So the value of the problem is increasing, going up, increasing, appreciating. All of those words are going to tell you that you're looking at growth. The number inside the parentheses needs to be greater than 1. That's your B value. Okay, so B needs to be greater than 1. Then you're looking at growth. Okay, remember back to the very beginning of our exponential unit, we had a standard exponential equation of y equals a times b to the x. B is the rate of change. So if your rate of change is greater than 1, then it's a growth thing. Now, over in decay, if you read words like going down, decreasing, declining, depreciating, all of those things mean decay. Okay? And then the other thing you can look at is the number inside the parentheses is less than 1. So B would be less than 1. Okay. So that's what we're going to use to determine here. So let's just take a look at a few of these examples. We want to look at the value that's being raised to the x power. So whatever the base is that's being raised to the x, that's our number in question. So if I look at number 6, I have y equals 7 raised to the x power minus 0.5. The thing that's being raised to the x power is greater than 1. 7 is greater than 1. So I would call this growth. If I take a look at the next one, now I've got y equals 5 times 2/5 raised to the x. The thing that's being raised to the x power here is less than 1. 2/5 is less than 1. So this is one where I'd call it decay. In number 8, I have y equals 2 times 0.75 raised to the x plus 3. 0.75 is less than 1. 0.75 is the thing being raised to the x power. 0.75 is less than 1, so again, I would call this decay. In number 9, I have y equals 1/2 times 4 to the x power. 4 is the thing being raised to the x. 4 is greater than 1. I would call that growth. And then the last one, number 10, I have y equals 10 times 5 to the x power minus 25. Again, the number that's in question is the thing that's being raised to the x power. So 5 is greater than 1, which means that this is growth. Okay. All right, that takes us to the end of our notes for exponential decay. Thanks for tuning in, and I will catch you next time.